Welcome to Arxflix. Today, we're breaking down an intriguing new paper titled Scalable High-Resolution Pixel Space Image Synthesis with Hourglass Diffusion Transformers, or HDiT. This research presents a novel image generative model that efficiently scales with pixel count, supporting high-resolution training directly in pixel space. We'll dive into the details and see how it bridges the gap between convolutional units and transformers. Here's a glimpse of the HDiT model's output. These images are generated directly in RGB pixel space, demonstrating what the model can achieve at resolutions of 1024 by 1024 on the FFHQ dataset and 256 by 156 on ImageNet. Let's explore how HDiT manages to scale so effectively. Diffusion models are now a prominent method for image generation. These models, like Stable Diffusion and Imagen, produce diverse and high-quality samples by reversing a diffusion process, usually defined by Gaussian noise. They can handle various modalities, not just static images, but also video and audio, showcasing their adaptability and robustness. The architectural backbone of diffusion models can vary significantly, ranging from CNN-based to transformer-based to hybrids and state space models. Each method has its pros and cons, especially when scaling to high resolutions. Latent diffusion, the current dominant approach for high-resolution image synthesis, often lacks fine detail and can complicate training with additional steps like cascaded super-resolution or multi-scale losses. Introducing HDiT, a pure transformer architecture inspired by a hierarchical structure. It improves efficiency while maintaining high image quality at megapixel scales in standard diffusion setups. Unlike typical diffusion transformers, HDiT achieves linear computational complexity scaling with the target number of image tokens. This diagram illustrates the high-level structure of the HDiT architecture. For any increase in target resolution, an additional neighborhood attention block gets added, allowing the model to handle high-resolution inputs efficiently. The paper's main contributions include adapting transformer-based diffusion backbones for efficient high-quality pixel space image generation, introducing HDiT for high-resolution image generation with subquadratic compute scaling, and demonstrating that HDiT performs well without requiring specific training methods for high resolution. This figure details the computational cost versus the resolution of HDiT B4 and the standard HDiT B4 model. HDiT drastically reduces computational cost at higher resolutions, less than 1% of the cost of comparable standard diffusion transformers. Natural images have hierarchical structures, making hierarchical models an intuitive choice. The HDiT leverages the hourglass structure, effectively shortening and re-expanding sequences. This method enables efficient global and local information processing, crucial for generating high-resolution images. The researchers tested HDiT on both conditional and unconditional image generation. High-quality images were generated from datasets such as ImageNet and FFHQ. 1024 by 1024 without relying on specific high-resolution training tricks. These samples from the FFHQ 1024 by 1024 model demonstrate HDiT's capability for generating globally coherent and detail-rich images. In comparisons, HDiT set a new state-of-the-art for diffusion models on FFHQ 1024 by 1024 and performed competitively on ImageNet 156 by 156. It outperformed baseline models in efficiency and quality without extensive preprocessing or multi-stage architectures. To sum up, HDiT offers a significant advancement in scalable, high-resolution image synthesis using transformers. With efficient computational scaling and robust image generation capabilities, HDiT sets a promising direction for future research in generative models. Future investigations could explore HDiT in latent diffusion setups for even higher efficiency and explore other modalities like audio and video generation. Thanks for watching. Don't forget to like, subscribe, and stay tuned for more deep dives into cutting-edge AI research on Arxflix. See you next time. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.